So, hello to everyone on the virtual jug, and this is session 2 of 24. Welcome, Heinz.
Hello.
And Heinz, today you're going to be talking about turbocharging CPU utilization in fork join using the ManagedBlocker. So, just previously we had a keynote with Venkat, so he's warmed the crowd up to a hardcore session now with fork join. So this is great. The sponsor of today's session is Heinz. Actually a recruiting company that work in Australia as well as other places, and the participating jug is the Melb JVM jug. So this is the second session out of 3 that they'll be joining the virtual jug for. So just a couple of quick notes about sponsors. So yeah, Heinz, recruiting talent at the forefront of digital technology. So if you're in Australia, if you're in Melbourne right now, you're sitting back, you're watching the virtual jug, but you're thinking, you know what, there's all this great technology, but what I really want is another job. I want to learn this technology. I want to use this technology. If you're interested in perhaps either a recruitment partner or looking for another job entirely, then perhaps contact John Paul. JP is a great guy. I talked to him on email and on the phone a couple of times. So do reach out to JP. He's a really friendly guy, and perhaps this time next week be looking at another job. So yeah, do check out Heinz if that's what you're interested for. Zero Turnaround are also the sponsors of the virtual jug in general. So a massive thank you to Zero Turnaround for pretty much making a lot of this happen. On this session, you can ask questions directly to Heinz in the Slack channel. If you go to vJUG24.com, just beneath the video, there's a link there to join Slack. And please join the live session channel, and there's discussion in there as well as questions. I'll relay those questions directly on the Hangout to Heinz. On Twitter, we have hashtag vJUG24, so please tweet with that. And if you're just joining us, please make sure your video quality is at its highest resolution. So on the bottom right, press the little HD cog and crank that up to the highest you can see. So joining us right now, if I was to jump back, stop sharing, and pop over to the Melbourne jug. It looks like everyone's back. Big wave from the Melbourne jug. Hello, guys. Good to see you there. And so yeah, without further ado, let me just hop straight over to Heinz, and we can. Hey, Heinz, there you are. How you doing?
Hi. Yes.
And whereabouts are you in the world right now, Heinz?
Well, I'm at home. You're at Crete, which is a really great pleasure.
Awesome.
It's also great to be speaking to Australia. That's where my grandfather grew up.
Oh, wow.
Yeah, so I was trying to figure out with my kids how long it would take to get from Crete to Melbourne, and I think it will take a while. Connor's come to Crete 3 times already for our Crete conference, so he knows it's a very long trip.
Oh, wow. Awesome.
We've had a couple of people here, so go over there. Yeah.
Oh, for Crete maybe, or?
Yeah, a couple of people come from here, go over to the Crete. So
yeah, awesome.
Yeah, good place.
Yeah. So I'm not going to have the Hangout open whilst I'm talking because I'll get distracted. So Simon, if you can just monitor it and interrupt me if there's a comment or a question, just read it out to me if you don't mind.
Absolutely.
You can be my text-to-voice simulator.
That's actually
today.
My best role, so that's good.
Not coffee, you mean? Not making coffee?
I can do that as well, but yeah, reading out loud is my best.
All right, let's get started. I only have a few minutes left before I've got to stop already. So we're going to look at how we can utilize available hardware better. And if you look at this graph, this is a CPU graph of my little MacBook Pro, and it's a 4-core machine, but it's got hyperthreading. So Mac OS X shows it as 8 different cores. Of course, it is only 4 real cores. And what you'll notice is at the beginning of the run, there's a fair amount of black in the graph. All right, a fair amount of black. And so what we want to do is we want to change that. So eventually we have mostly green. So we're going to have this type of graph where it's mostly green at the beginning, and also to improve our performance. So in order to utilize our hardware, we want to do a bit of work that's actually going to utilize, and it's going to take a bit of effort to number crunch. So we're going to do the famous Fibonacci series. It doesn't have very many practical applications unless you are in Australia and you want to figure out why were there so many rabbits, right? And it's a simple Fibonacci series reason why you had so many rabbits. You know, one pair makes another two pairs, and those two each make another two pairs, and etc. And it grows really quickly. So the numbers get big, and when something gets very large in computing, we struggle with it. So if we wanted to have a very naive implementation, we could take the mathematical definition, and we could simply implement it as Java code, where we say public long f, if n is less or equal to 1, return n, otherwise return f of n minus 1 plus f of n minus 2. But the problem with this naive implementation is that it's essentially got computational complexity of a Fibonacci series. And as I said before, the numbers get very big very quickly, and so it also gets very slow very quickly. So this is not going to cut it. This won't be very useful. And there's a book on Java performance. I won't mention the title. And in the book, they've got this definition, and they mention something like, well, if you're working at Fibonacci 100, now, if you have this definition, Fibonacci 100 won't complete in our lifetime. Even if we get really old, it will never complete. Well, not in our lifetime anyway. So we need a better algorithm. So we could try it iteratively. So we don't do the work over and over again, but instead we work out every number only a single time. And this iterative algorithm essentially comes up with the same answer at the end, but it is a lot quicker. So you can work out Fibonacci 1 billion in 1.7 seconds. However, the long overflows when n is 93. So even though we get the answer quickly, the answer is wrong. So that doesn't really help us. So the obvious choice is to take BigInteger. But BigInteger, the add function of BigInteger is also linear. So you've got a linear algorithm, and you've got a linear add, and linear times linear gives you quadratic. So we end up with basically a bubble sort, which is okay for smallish numbers. But as n gets larger, you can't calculate it. So you could work out Fibonacci, for example, of 1,000 and 10,000 and maybe 100,000. But once you get to in the millions and in the billions, it's going to take simply too long to calculate. The third attempt is to take a better formula. And just to give you an idea, the first formula we had, which was this one over here, if we tried to work out Fibonacci of 1,000 with that, it would take approximately 10 to the power of 200 years to complete. So that's a very long time, 10 to the 200 years. And with this algorithm, we can work out Fibonacci in a few milliseconds of 1,000. So it's really fast. And the formula itself has got logarithmic time complexity, which is always attractive when we can get that. And the multiplier used to be order n squared, but nowadays they've got two better algorithms. If the numbers get large, the one is Karatsuba, and the other one is a three-way Toom-Cook. And Toom-Cook is n to the power of 1.465. So you have much better complexity than before. Now, the multiplier in BigInteger is still single-threaded. And we're going to fix that a bit later once we get to it. Now, we implement this algorithm using BigInteger. And this is the formula, and we'll do this in code, and I'll show you how to do it. As I said, if we stuck with the original code, it would take an incredibly long time to complete. So this is my original, and if I ran this, you can run it for small numbers. That will work. For example, here's my Fibonacci test. I've got simple values, and if I run that, it's going to complete. It's going to say, yes, this is in fact correct. But if I did Fibonacci 1,000, this would take 10 to the 200 years, and who's got time for that, right? We don't have time for that. So let's go back to the code, and we're going to now implement the Fibonacci series using Dijkstra's sum of squares. So if n is 0, it's 0. If n is 1, it's 1. And then we essentially divide n into half. So we say int half equals n plus 1 divided by 2. And we then say if big integer f naught equals f of n minus 1 and f of n by itself. So at each point we're dividing by 2. So this gives us the logarithmic time complexity. And then if n is odd, then we've got the one formula where we add the square together. That's this one over here. And so this is going to become return f of naught dot square, which is basically multiplied by itself. And then we add to that f of 1 multiplied with itself again. So that's f naught squared and f1 squared. There is actually a square function in BigInteger, but it's private, so we can't call it. So we have to do it this way. Else, we're going to say multiply f naught by 2, and there's a simple way to do that. We just say shift left by 1, right? Then we add f1 to it, and we multiply the whole result with f1. And if I did everything correctly, I've done this once or twice this year, then it should calculate Fibonacci 1000 quite fast. So if you run this now, let's run it and see what comes out. And I have made a mistake. Okay, so I was in too much of a hurry. So let's go back to the code. And we need to yes, I must say half, not n. So I mustn't hurry so much. We've got the saying in our household, less haste and more speed, right? It's basically, you can really hurry, but if you want to go very fast, you need to slow down. And one of my friends, Stephen Chin, is very good at setting up all sorts of very complicated equipment, and he always goes very slowly. And I was thinking of him this morning, thinking I should slow down because otherwise I'm going to make a mistake. And there we go. It worked at Fibonacci 1000 in like 4 milliseconds as opposed to 10 to the 200 years. So you can see that it's much better. Fibonacci of 100 million is a massively large number. It's bigger than the continent of Australia. Okay, maybe not, but it is very, very large. And so what we're going to see is how long it actually takes to work it out. And it's a single-threaded test at the moment. It's a bit difficult to see because I've got Hangout running it as well. And Hangout is going to use up a substantial amount of my resources. But we're going to do our best with the performance. Now, what I've done is I've actually reduced the amount of parallelism on our system a bit. I'll talk about this in a moment a bit more. At the moment, everything's single-threaded, and we ran in 53 seconds for this Fibonacci series. So we'll talk about the parallelism in a moment. Let's just write this down. This is Fibonacci of 100 million, taking 53 seconds. Now, it's single-threaded, which is, we should be able to see if we run it and start top, and we should see that Java here is never goes above 100%, right? Or very seldomly. It might go over 100% if the garbage collector runs, but generally it's sticking below 100% because I've only got one thread which is actually running. So let's stop that test. We've done enough. And let's go on to the next improvement we can make to this algorithm, and that is to parallelize the algorithm. Now, the important thing to know here is that you don't actually need to understand how the algorithm works. All you need to figure out is how you can sort of divide it in two. How can you divide the work that needs to be done into two distinct chunks? And in our case, it's quite easy because we're doing f of half and f of half minus 1. So we could actually take one of those, one half, and send it to the fork join pool to do. So we're going to implement something like this, where we take the first half, the f half minus 1, and we execute it inside a recursive task. So we create the recursive task, we call fork on it, and this will now fork it into the fork join pool. It will actually execute it inside that pool, and then once we've worked out the second half of the number, then we would join with the first half. Now, just keep in mind that this is a that this is a recursive method call. So at every level, we're going to create more and more forks. We're going to have quite a few forks, and we should be able to keep all our threads quite busy. So our threads should be running at 100% CPU, and all the CPUs should be busy at the same time. Let's implement this and see how it improves our performance. At the moment, we're at 53 seconds for the run. So let's do this again. And we're going to take the first half and wrap it inside a recursive task of BigInteger, which will be the if naught task equals new. We make an anonymous in a class, and inside there, we put the code that we had inside here. So return f of half minus 1. And then afterwards, we fork that. So we say if naught task.fork. And then we do the second half, and once we've done the second half, we then join with the task. Then the result comes back. Now, instead of just having one thread busy, we're going to have 4 threads busy. And now I'm getting back to what I said before, that I've sort of brought down the parallelism. You see, I've got 4 cores, but with hyperthreading, Java by default would give it 8 threads to do the work. And that's not really fair because I only have 4 cores. So we're going to do this with the parallelism of equal to 3 in order to only give it 3 threads inside the common pool, plus the submitting thread, the main thread, will also work. And so what you'll see now is that all the threads will be busy doing this recursive task. And we should be running faster as well. So let's just go and look at top. Top is look 400% CPU. That's what you want. So that's great. And you notice that after a while, it's gone down to 300%, down to 200%, and now it's down at 100%. So it started well. Our whole run started well, and I've got a graph of that as well. Let me show you the graph. The graph is quite insightful. You can see here how the graph, at the beginning, we were running 100% CPU, or 400%, which is 4 CPUs at the same time. And then after a while, it sloped down. So, of course, the question is, why does it do that, and what's the total time? Well, the total time is now 31 seconds, 32 seconds. And it's not actually as good as we were hoping to do it. So this is now the second run. This is with the recursive task. So we've parallelized our Fibonacci. The first wave we've got base to sum of squares. Then we parallelize Fibonacci. So it has become faster, but it's not 4 times faster. We wanted it to be 4 times faster, but it's not 4 times faster. So the question is, what can we do next? So how can we improve it further? Before I show you that, I want to give you a very special thing, and I've posted it into the chat room. And that is, I've got a course, a mini course on Java 9, where we look at how Java 9 works with non-blocking network communication. And if you go to this link, it's only for those who are actually listening live. If you're not listening live, sorry, you're out of luck, because this will expire at the end of this talk, so it won't work anymore once the talk is done. But if you're listening during the talk, we reward you for your diligence of waking up early and being at the talk. And you get a free subscription to my newsletter, and also a free license, which is worth €60, to this mini course on Java 9. It's using Java 9, some features from there, and it does some non-blocking communication. All right. So the problem we had before was that whilst we've parallelized our Fibonacci algorithm, we haven't parallelized the multiplier. And you can see this quite clearly when you run the code, because in the beginning, when you run it, let's capture a few thread dumps. We need to do 2 thread dumps here. One, and I'll wait for a little bit, and I'll do another thread dump. And then I'll wait a bit longer, and near the end, I'll do one more thread dump. We just see what if we are. Once CPU hits 100%, I'm going to do one more thread dump. So now we do one more thread dump. And what we can now see, if you look at the thread dumps, is that in the beginning, when we first started with this run, we had 1, 2, 3 threads, worker threads runnable and working, and the main thread was also runnable working. So 4 threads were working on the problem. That's why we had a 400% CPU. And then after a while, we had 1 thread runnable and 2 threads runnable, 3 threads runnable. Okay, I think we still had 4 threads runnable. Yeah, we still had 4 threads runnable. But then when we got to 100%, let's see what the threads were doing. This was towards the end. You see here, we've got the common pool worker threads are all just waiting. They're all parked, waiting on some condition. And the only thread that's doing anything is our main thread. Now, the reason for that, and you can see there's this recursive method called to do Cook and Karatsuba. The reason why this is happening is that when you do recursive decomposition, you often have to merge the results together. And in that case, the merging is happening over here when we're doing the multiplications. So the multiplications in the end start to dominate the whole algorithm because the numbers get very large. So what we can also do is we can try and improve the way that BigInteger works. At the moment, BigInteger works like this, that it's all single-threaded, and they've got 3 different algorithms. They've got the traditional order n to the power of 2 algorithm, and then if the numbers get too large, then they go over a threshold, and they then go and get multiplied with Karatsuba. And if they get even bigger, then they get multiplied with Cook. So Cook is for very big numbers, and we want to make those big numbers faster. So we're going to improve BigInteger by parallelizing it. Now, a few years ago, I figured out how Karatsuba worked. I sort of understood that algorithm, but I've never tried to understand Cook. So what I want to do is I want to hack the BigInteger to make it parallel, even if I don't understand how BigInteger actually works and how the Cook actually works. So the way to do this is to take BigInteger, Control A, Control C, right? This is a way to write lots of lines of code very quickly. And then we copy it into java.math. And inside here, we've got multiply Cook and square Cook. So let's start with multiply Cook. We're going to do, it's very similar to what we did just now, where we had anonymous in a class for the recursive task, but this time we're going to make an inner class, a private static class, multiplier task, extends recursive task of BigInteger, and inside I'm going to have a BigInteger A and B. So we're going to multiply those, pass the constructor A and B, and the compute function would now multiply these 2 together. So we're going to say return A.multiply and B, like so. All right. And then this multiply is used inside here. So where we've got the multiply, sorry, excuse me for a second. No, sorry, I thought I was muted, but I just see I wasn't muted. I apologize for the loud coughing. So here we're going to have 2 multiply tasks. The first one's going to be for V0, task equals new multiply A0 comma B0. The second multiply task is going to be for V1. So V1 is going to, this one's going to be DA1 and DB1. So this one's A0 and B0, other one is DA1 and DB1. Now, when we create the task, we also want to say V0 task.fork, fork it. And then we do the second half, which is the second multiply. And before we do the third multiply, we say V0 equals V0 task.join. So we join it up again to get the values back. And we do the same thing for V1. We're going to say V1 task.fork. Then once we've done everything else, all the other multipliers, we're going to say V1 equals V1 task.join. So we fork the one task, we then do the second task, then we join the first task again, and after that we would go and fork another task, do the second and actually the fourth and fifth multiply, and once I'm done, I would join with the V1 task and generate that. So this is how you do the multiply. Again, I have no idea how this actually works, this algorithm. It's really complicated. But even though I don't understand it, I can still parallelize it. So I've got the square term cook. We would do essentially the same thing. We're going to make a private static class square task, extends recursive task of BigInteger, and then in here we're going to have one field, private final BigInteger A, and the constructor, of course, and then the compute function would say return a dot square. So the square function is, of course, available inside the class because it's a private method. So we'll use the same. We'll do the same sort of process again. We've got 5 squares, 1, 2, 3, 4, 5, and before the first square, we're going to say square task v naught task equals new square task of a naught. So v naught task dot fork. And after we've done the second square before the third square, we're going to say v naught equals v naught task dot join. Then the same thing for v1. It's going to be a square task of v1 task equals new square task of da1. I'm not going to make any mistakes. I'm trying to go so fast to get through all my material. I'll show you all the cool tricks. And then after we've done the other squares, we're going to say v1 equals v1 task dot fask. v1 task dot join. So we just get rid of the sort of here. So I think this is correct, and we'll run it and we'll see if it improves the performance. So we should now see that Java should stay at roughly 400% throughout the system. It won't always be exactly 400, but it's going to hopefully be pretty close to 400 throughout the run. And that means we are utilizing the available hardware. Okay, there's a bit of single-threadedness still going on, but in fact, nothing's changed. And the reason nothing's changed is because I've made a mistake that I very often do, is I'm not actually using BigInteger, right? You need to also use it. It's not enough to simply hack it. You also have to use it. So we can verify whether we're using it or not by, at the top of the class, printing out a message and then checking that that message is being printed out. So let's say static, we get to say here, using hacked BigInteger. And you'll see that when I run the Fibonacci test now, that is not printed out. So I'm not actually using the hacked BigInteger, right? So this is why the test is running exactly like before. Now, the way to do that is with a property. So you can say, and I mentioned this also in the slides, -x boot class, I had it at /a, which means append, but if I prepend it with /p, then it's going to allow me to use my hacked BigInteger as the BigInteger. See, now it's using the hacked BigInteger. And now we should see that CPU stays closer to 400% throughout the run. So that we can see, okay, it's not exactly 300%, but it's a lot closer than it was before. So before we were running at 100%, and now it seems to be going, and it actually completes faster as well. So our total speed for this run is 19 seconds. So of course we do lose a bit because of overhead, but we have improved it quite a lot from when we started. This is now a parallel multiplier. Okay, now if we look at the actual algorithm again of how Fibonacci works with the extra sum of squares, these are the numbers that need to be calculated in order to get to Fibonacci 1 million. And you can see that there are lots of duplicates. For example, on the first level, you just have 49999 and 500,000, but on the second level, you can see that 249999 actually appears twice, and 250,000 appears twice. So we're doing lots and lots of duplicate work. And what we can do is we can maybe cache the results. And this should also improve our performance quite substantially. Towards the bottom, like Fibonacci of 60, you need to work out 8,000 times. So there's lots of duplication going on. So what we'll do is we'll add a cache. Now, one thing that a lot of people do is they want to use the computive absent method for this. So it's basically they put in a cache, and then that just use computive absent. But computive absent doesn't work if you've got recursive updates inside the function. So that won't work. So we have to do it the old-fashioned way. So let's have two methods. One is going to be called f with an n. The other one's going to have a map from integer to big integer called cache. So these are the two different methods, and we'll set this up, this integer cache up here equals new. It's got to be a concurrent hash map because it's going to be accessed from multiple threads at the same time. And we then seed it with two values, cache.put 0, and cache.put 1, 1. So we seed it with those two values. And we also want to have this at the top, so we don't have to check that all the time. And then we can say return f of n, comma, the cache. We don't need to check for 0 anymore. And inside here, we're going to call f, comma, half, comma, cache, and f half minus 1, comma, cache. We each time are delegating through to this new f method. And then, of course, we need to cache the data. So we need to say big integer result equals cache.get of n. And if result is null, then we work it out. So this is sort of almost like the perfect example of where we could use computive absent, except it doesn't work because we're doing a recursive update. So we can say here result equals and result equals, and then afterwards we can say cache.put n, comma, results, and we can return the result. So this is essentially I've done the computive absent by hand over here. So I'm first checking, getting the value. If the value is null, then I work it out and I put it into the cache and return the result. So we're running at 19 seconds just now. Let's run it again. And we should actually still have 400% or so of CPU, so throughout the system. And it should be a lot faster because I'm not doing so much duplicate code anymore. So let's see how long that runs for. Hopefully it'll run up, and it's done already. So we shaved it down to 14.5 seconds. So that's fantastic. So we've got now down to a much better value. And let's also print out how long each of the actual multiplications take, because I think that's going to be quite interesting too. So if you look at this, we could put a timer around this multiplier. So let's do that. Let's put time equals system current time millis before, and then after we've worked it out, we print it out with the timers. But we don't want to do this for very small numbers. So we'll say only if n is bigger than 10,000 do we care. Otherwise, we just make it 0. We do the same thing here. Only if n is bigger than 10,000 do we care about the time. Otherwise, we just keep it at 0. And if n is bigger than 10, in fact, if time is bigger than 50 milliseconds, then you print out the time, because we don't want to know about we don't want to worry if it's 5 milliseconds. We don't want to worry if it starts getting substantially expensive. So we're also going to print out what Fibonacci we're actually calculating here. So for what Fibonacci we have the time. So let's run this again, and now we can see how long everything takes. You can see that if you look at the numbers, it's quite interesting because even though we've got this cache, we are still working out quite a few of the numbers multiple times. Here, for example, 2499999 is done twice, and both cost 2.7 seconds. So this is kind of silly. Why are we actually wasting our time working it out if there's somebody else working it out as well? And a question we can ask is, why is this happening? Why are we working out 124999 3 times when we actually have got a cache that's trying to avoid this? And the reason is quite simple. If you go back to this diagram, you see over here, we've got the numbers which are the same are at the same level. So there's a very high probability that the different threads will actually encounter the same number at roughly the same time. And because the numbers take a while to calculate, it's very probable that they actually will have this type of effect. So let's do something else. Let's see if we can not just cache the results, but also to see if we can make a reservation so that we don't accidentally have 2 threads working on the same number. Okay, so let's try that. This is now our 4th attempt. And basically, we do something which we call a reserved caching scheme. We define a special big integer. We'll call it reserved. And this reserved is going to be BigInteger.value of -1000. And -1000 will be used as a special signature to say that somebody's working on it. So instead of calling cache.get, I'm going to say cache.put if absent in comma reserved, right, like so. And then if the result is null, that means that I'm the first thread that wants to work this out. No one else is working on this particular problem at the moment. And so I can start working immediately. You see, put if absent returns null if nobody had put something in there before. Null is essentially what was there before we started. And then what we do is we can say else if result is equal to the reserved field, then we can say something like while result equals cache.get of n, while it's equal to reserve, whilst it's still reserved, we're going to say we're going to wait. Now, what do we wait on? Well, in this case, we're simply going to wait on the reserved object as our field, and we have to worry about the interrupted exception. So let's do that. Let's catch that and say, if we get interrupted, we're going to say throw a new cancellation exception, say that we've been cancelled. All right. So we also need to synchronize. So we need to stick this one to synchronized, synchronize on reserved. Then when we put it in, we need to synchronize that too. And the synchronized here would be on the reserved. And after we've put it in, we'll say reserved.notify anybody who cares about this. So reserved.notify all. So this way, if somebody else is working on it, we'll get back the reserved, and we don't start working as well. We simply suspend the thread. Let's run this and see what the performance is like. Now, you can see that we are only working out every one a single time. So it should be a lot faster than what we just had. So before, we were running at, what was it before? Before it was running at 14.5 seconds. Now it should be much, much faster than that. And it is a bit faster, it is a bit faster, but not as much as I was hoping. And one of the reasons why it's not that much faster is if you run this again, and let's take a thread dump. Oh, wait, I must have pressed the wrong button there. Let's do that again. Take a thread dump. Especially at the beginning of the run, you'll notice that I've got one thread working, which is runnable, which is good. And then I've got another thread waiting. This is waiting for another thread who's working on the same value. And again, the probability of this happening is quite large because of the way that the numbers get split. Another thread is waiting, sorry. And the main thread is also waiting. So actually only one thread is really doing any work. It's a bit like supervisors watching their workers doing the work. And you can see here that the Java performance is not reaching 400%. Now it's 100%. Okay, now it's 400%. It does reach it eventually, but in the beginning of the run, there's a pretty good chance that you're not going to use up all the available hardware. So this is, of course, a bit of a problem. So what can we do about it? Well, the fork join pool has got support for managing any method which might block. Now there's a special interface called ManagedBlocker. What this does is it essentially wraps the code that does the waiting. So the code which does the waiting would be now managed by the fork join pool. And if the fork join pool sees that it needs to be suspended for whatever reason, if a thread has to block, then it can construct another thread to take its place in order to keep the parallelism high. So we want to have a parallelism of 3, because I've got 4 cores and the main thread also works, and the fork join pool can do that together with the ManagedBlocker. Now there are 2 classes at the moment in Java that support or that use ManagedBlockers. The one is the phaser, which is like a new countdown latch / cyclic barrier from Java 7, and the other one is completable future, which we'll talk about in the next demo. So let's try that out. This is now this was reserved, the reserved caching scheme. Now let's try having a ManagedBlocker. So what we do is the code that waits, this code over here, we're going to wrap inside an object. So this is going to be, let's copy that. We're going to make a private class reserved blocker, implements ManagedBlocker inside fork join pool. And there are 2 methods, block is releasable and block. And is releasable is basically this over here. So it's your result. It's if cache.get equals reserved is not equal to reserved. We need to have the int end, and we also need to have the cache as well. So it's basically these fields we need. It's going to be private final cache. This haste more speed, and the constructor for those. We also need the cache, the result as well. That's going to not be final because we're going to change it. BigInteger results, like that. So what we now do is the is releasable is going to be return results equals cache dot get of in, and if that's not equal to reserved, if it's not equal to reserved, then it means that we can actually leave from the reserve blocker. So we can say whilst not is releasable, this. Now, one thing which is important here is when I call result equals cache.get, cache.get is either going to be reserved or it's going to be the correct result. And if I call the correct, if I call it and it gives back the result back, if I call it a second time, it will simply give back the results again. So we don't have to check whether or not result is maybe not reserved anymore. So, but we could say if result is not equal to reserved or result equals cache.get is not equal to reserved. We don't need that in this case, but in other code, if the method here was going to change the state, then we would need something like this. So I'll leave it in because it's not harmful. So either if the result's not equal to reserved or we read it into the result and that's not equal to reserved. Okay, so so here we're going to say return true with the block, because once we actually get to the block, we will always be released. Okay, now we would over here we'd say managed the reserve blocker. Blocker equals new reserve blocker within comma the cache, and then instead of saying blocker.block, we're going to say fork join pool dot manage block and pass in the blocker, and then result equals blocker dot result. Now the only thread that's actually writing the result and reading it is the main thread. This is why we don't need to make result volatile. we can leave it as a plain field. Let's run it again. This is now with the reserved blocker. And I've made a mistake somewhere along the line. Where's my mistake now? Somewhere's a null. Oh, no, cache. Reserve.wait. Let me take this out because I don't normally have that in there. I don't think that's the problem though. There's a problem. Okay, I made a mistake somewhere. I said, oh, okay. Yes, sorry. There's one more. I need to say if results is equal to null, or I'll leave this out. It's not necessary in this case anyway, and I'm just complicating it for myself. And I don't have time to be complicated because the next crew is coming on in a moment. So it's now running with the managed blocker, and you can see it now finished even faster, 20% faster at 10.126. So that's a very nice improvement that we had over the previous. So we've actually made it altogether about more than 5 times faster from when we started. This is with the managed blocker. I want to run it once more quickly and get some thread dumps. There's a thread dump, and you'll see now in the thread dump that we have one thread waiting, another thread waiting, another thread waiting, and then we have one thread runnable. That's one. So 4 waiting, 1 runnable, and another waiting. So it still happens sometimes that we've got more threads, but don't forget that this is that I now have more threads being constructed. So if I run this again, and you look at top, let me just do this a second time. Run it again. You should now see that that top stays closer to 400% right from the beginning. So that's awesome. And overall, you actually get better performance as well. So this is the end of this talk. There's one more little thing which is homework for you. You can also do this with Completable Future, with then accept both async and complete. The challenge is what happens when you disable the common fork join pool. You might get some very weird results. So if you want to try this, please do, and send me results to heinz@javaspecialist.eu. I write a Java Specialist newsletter, and also I mentioned at the beginning of this talk that I've got a special for you guys, those that are listening live. If anybody's listening live or hasn't jumped out of the building yet, there's a free subscription to my Java Specialist newsletter, and also a free license to my latest mini course on Java 9 using Java 9. And you simply go to tinyurl.com/vJUG24, and you can get it there. So do we have any questions? Let me see if there's any questions here.
So that was the link I've actually put into the Slack channel. The Slack channel is the one that we're actually live on. So I've put it in a couple of times actually. So yeah, do definitely go to that. I'm sure that's an amazing course. And also the JavaSpecialist.eu. I can't praise that newsletter highly enough. It's one of the best newsletters in Java. So do make sure you've signed up to that, everyone on the virtual jug. So we're going to jump straight over to Melbourne. Well, I ask everyone to type any questions into the live session Slack channel. I'll jump over to Melbourne to see if there's any questions there.
All right, Rowan, go ahead.
Yeah. Why do you synchronize on the reserve value and not on n? Because if two threads calculating for like 20 and 40, like they don't need to wait for each other. Like,
yeah, that's a good one. You can't synchronize on n because n is going to be an integer wrapper, right? So if you synchronize on that, then it's a primitive, right? So you can't synchronize on that anyway. But what you could do is you could have a different reserved object for each different case. So you could do that. You could say, for example, that if the reserved value is negative, then you could use that instead of using instead of doing just having one class. but that's not our bottleneck. Our bottleneck is not on contention on there. And so that's why I haven't done it. Let me quickly show you how that code would look. And I think that's the right one. So basically, if we get rid of this reserved, and we say, put if absent, for example, BigInteger dot value of minus n, right? So we put in a minus n. Then we can say if results dot compared to 0 is less than 0, so if it's negative, in other words, then you do this reserve blocker, right? And what you need to do is pass in the result as the lock. And then you could use that this object. Okay, we need to actually put this into a field. Let's call this reserved as a small. Sorry, this reserved. So we can say synchronize on reserved, right? And reserved.notify all. And so we're going to pass in reserved here as well. So if it's less, so let's change reserved blocker. Because this will have the reserved. And we'll create a field for that, reserved. And that means we can get rid of this other constructor. So just this one. And we need to also assign the other fields in there. So we're going to say, let's rid of that, let's make a new constructor. So it's going to be a constructor having those 3 fields. And then whilst it's not equal to reserved, we're going to use reserved, a special field here instead of having it one for each. So instead of sharing it, we've got one each. But that's not the bottleneck. So we're not going to get a substantial improvement in performance, I don't think. Right? It's actually hard to know because and also there's a mistake here. Yeah, there's another mistake which I need to just correct. Somewhere along the line, I need to make sure that it's actually, maybe the 0 is the wrong way around. Result compared to 0. If it's, yeah, I'm not sure now. So my point is, you could do something like that. There's a bug in the code somewhere along the line. But let's see what the performance is like. Even if the answer is not correct, it doesn't actually show because there's a mistake. This is to draw off unit tests. So somewhere along the line, I've made a mistake. Oh, because 0, of course, you could have 0, I guess, but 0 should be covered already. Anyway, that's the general idea, is to have a different reserve per instance, or to maybe even say not value of -1, but let's say value of minus 10,000. So it's always going to be a new instance. And if you do it this way, and then we can say, if compared to BigInteger.value of minus 1,000, 10,000, or if it's equal to that, then you would exit from here. So if this equals that, then you'd go into here. And then as long as it's equal to 10,000, then you're going to retry. So it still doesn't work. I've got some bugs in it, but you get the general idea. I'm not sure what the performance difference will be. I don't think it'll be much more. All right, any other questions?
None over here.
I got a question in from Slack, from Mimic47, asks, is there a next level, a deeper level, where you try to force SSE, for example?
SSE? What is SSE?
I can ask for that. I was hoping you would know. I thought it was me.
Some random TLA that I don't know. Secure socket extension.
I think it is processor instructions which make it faster for certain math.
Oh, okay. No, I don't know.
That was an easy one then. Okay, so no other questions right now in Slack. We've got a few minutes till the next session, so I'll just say a massive thank you then to Heinz. A great session, and I do recommend everything that Heinz does offline as well with the newsletter in particular. So I would recommend everyone sign up to that. Very, very interesting. It's the deepest newsletter you'll read, I'm sure. So
there's one more thing I want to just mention, if there's no question about that. That is that when I first started doing this talk, I used to copy BigInteger into a different package, and I started copying it into, and then one day I copied it into Java Math, and it was noticeably faster in Java Math than in any other package. So that's an interesting puzzle, and you can try and figure out why that would be. There is a logical explanation why that would be.
Always designed as coded, huh? Awesome. So our next session. So yeah, massive thank you to Heinz Kabutz.
Thank you very much.
Thank you.
Thanks, Melbourne. Thanks for joining.